So now we want to combine our thoughts on the shapes of molecules and the polarity of molecules and learn about intermolecular forces of attraction. How are molecules, how do they interact with other molecules? How are they held together, or how are they not held together? So intermolecular forces are defined as forces between molecules, and the macroscopic properties are determined by the type and strength of the force. For example, the boiling and melting points of substances determined by the types of intermolecular forces that are present. The viscosity, solubility, density, also determined by the types and strengths of intermolecular forces. And the 3D shapes and functions of DNA and protein. These are topics for later chapters in our book. It's important to note that intermolecular forces are much weaker than covalent bonds. So we're not talking about covalent bonds here. We're just talking about forces that are present, much weaker than covalent bonds, but lend a lot to the macroscopic properties of the substances. So they might be only 5 to 10% as strong as a covalent bond, but they're important because they're very abundant. There's lots and lots of intermolecular forces present in larger molecules. As I said before, they determine many macroscopic properties, and they give functionality to most biological molecules. These are how proteins interact with each other, through intermolecular forces. So there are 3 types that we're going to discuss. In order of increasing strength, the weakest are called dispersion or London forces. The next weakest are called dipole-dipole forces, and then the strongest of these 3 intermolecular forces are called hydrogen bonds. And in order to decide which is present, again, we need a proper Lewis structure, and we need to identify whether the molecule is polar and which bonds are polar. So deciding which is present is not hard. First thing we ask ourselves, are polar molecules present? If the answer is no, the only force that are present are dispersion forces. These are present in all molecules. So every molecule will have dispersion forces to some extent. If you answer yes to the all are polar molecules present, then the next question is, are there HO or HN bonds present? If it's no, then we have, in addition to dispersion forces, we have dipole-dipole forces, because it's a polar molecule. If there are HO or HN bonds present, then we also have hydrogen bonding forces. So the forces build up from dispersion forces to then include dipole-dipole forces, and some specialized molecules that have HO and HN bonds will also have hydrogen bonding forces, so they will have all 3 types of intermolecular forces. Clicker question 3.6, a little bit of a review. Which molecule is most polar, HCl, HBr, or HI? So when faced with a question like this, it's important to ask ourselves, what is the difference between these 3 molecules? All have H's in them, and all have a different halogen. And we know that chlorine is closest to fluorine, bromine is in the middle, and iodine is at the bottom of group 7A. Here's group 7A. Iodine's at the bottom, chlorine is near the top towards fluorine. And so the difference in electronegativity between these 3 halogens is that chlorine is the most electronegative, iodine is the least electronegative. And so chlorine is going to have the strongest pull on the electrons, and that leads to HCl being the most polar molecule, because we have the strongest electronegative element present in HCl. So, first type of force are dispersion forces. And imagine some nonpolar molecules floating around in their container. By random chance, a temporary dipole would form in one of those molecules. Remember, a dipole is where we have a region of negative charge and a region of positive charge. So a temporary dipole forms, and this influences all the molecules surrounding that molecule with the temporary dipole. Then we have induced dipoles forming in all the surrounding molecules, and those induced dipoles will line up so that positive is near negative, negative is near positive. They'll line up in order, and they feel some forces of attraction. These are called dispersion forces, and this keeps these molecules connected together or interacting a little more closely than they would if there were no dispersion forces. Again, every molecule has dispersion forces as long as there are electrons in the molecule. The more electrons that the molecule has, the greater the dispersion forces. And so they're called dispersion forces because the effect is distributed throughout the sample. And dispersion forces can increase when the number of electrons in the molecule increases, and also when the surface area of a molecule increases. Surface area could be thought of as a molecule shaped like a baseball bat versus a molecule shaped like a basketball. If I bring two basketballs together, they can touch on a small area of the surface of that basketball, right? They can touch on a very small area. If I bring two baseball bats side by side, they can touch all along the side of the bats that is touching the other bat. So all along that one edge. Whereas on the basketball, it's just a small area of the surface. And so larger molecules have more dispersion forces than small molecules because larger molecules will have more electrons. And this leads us to the idea that the larger the molecule, the higher the boiling point. The higher the boiling point is higher because it has more dispersion forces holding those molecules together. So if we compare hexane, which is a nonpolar hydrocarbon, to ethane, which is also a nonpolar hydrocarbon, but it's much smaller than hexane, at room temperature, hexane is a liquid, but ethane is a gas. So ethane has already boiled at room temperature, and the molecules are not held together very strongly, certainly not as strongly as hexane are, because there are a lot more electrons in hexane. Each of these carbon-hydrogen bonds contains 2 electrons, whereas there are much fewer carbon-hydrogen bonds in ethane. So the bigger the molecule, the stronger the dispersion forces. The next level of intermolecular forces are the dipole-dipole forces. And those are when we have polar molecules. So now it's important to be able to recognize if our molecule is polar. Hydrocarbons are not polar, but molecules that have different types of bonds in them, like formaldehyde here, are certainly polar. Here's the electron density diagram. Blue is lots of partial positive charge, and red is the partial negative charge, and we can abbreviate that even further with our generic dipole shape here. So polar molecules show dipole-dipole forces, and that's because they have a permanent dipole, not an induced or temporary dipole like in dispersion forces. And so these are much stronger than dispersion forces because the dipole is always present, and they will line up always in this order where the dipoles are touching negative to positive, negative to positive. And so this lends formaldehyde to have a much higher boiling point than you might expect from its small size. Because it has this permanent dipole, they are always interacting in this manner. So then we get to the third type of intermolecular forces, and that's called hydrogen bonds. It's a special type of dipole-dipole force present only when we have HO, HN, or HF bonds. Of course, they are weaker than covalent bonds, but they are the strongest type of intermolecular force. Water has hydrogen bonds, and that lends water to have a very high boiling point for its very small mass. It boils at 100 degrees Celsius, even though it only has 2 H's and an oxygen. This drawing here shows the hydrogen bonding in water, where the oxygen is partially negative, the H is partially positive, and that partially positive H will interact with other partially negative oxygens on different water molecules, typically using the lone pair on the oxygen to interact with the hydrogen. We show a hydrogen bond as a dashed line. It's not a full bond, of course. It's just an interaction of a hydrogen on an adjacent molecule with the lone pair on the oxygen. So we find hydrogen bonds all over the place. There are many biological molecules that contain OH or NH groups, and these are proteins, carbohydrates, DNA. They typically form hydrogen bonds with other similar groups, either themselves or with water. And we're going to talk about all 3 of these in their own chapter later on in this textbook. So some consequences of hydrogen bonds. Water has a surface tension that causes it to bead up on different surfaces. It doesn't just spread out and completely wet the surface. If we put a drop of water on the table, on a glass, or on this leaf, it typically forms a partially spherical drop. Also, when water freezes, the ice, the solid water, has much order in it, and that results in a lower density, which means that ice floats. We know that ice floats. We've seen ice cubes in our glass of water. We know that icebergs float on the ocean. And actually, this is a rather unique property of water. Most other compounds, if they have a solid in the liquid form, that solid will sink. So if we have a chunk of solid iron in liquid molten iron, that iron is more dense and it will sink to the bottom of the container of liquid iron. As I said before, the hydrogen bonds in water cause water to be a liquid at room temperature, while the similarly sized methane, CH4, methane has a mass of 16 grams per mole, whereas water has a mass of 18 grams per mole, so it's very similar. Methane is a gas at room temperature. It has a much, much lower boiling point because it's completely nonpolar. It's a hydrocarbon with only dispersion forces present. So let's look at these practice problems. First one, which type of intermolecular force is the weakest? Hydrogen bonding, dispersion, or dipole-dipole? So this is just something you have to memorize. Certainly dispersion is the weakest. And we remember that hydrogen bonding is the strongest. So a molecule might have just dispersion, it might have dispersion and dipole-dipole, or it might have all three. It would never just have hydrogen bonding or just have dipole-dipole forces. Next question, what force of attraction holds hydrocarbons together? Well, remember that hydrocarbons are like methane, CH4. They have only carbons and hydrogens, and so there's no polarity. There's no OH bonds, there's no NH bonds, so it's only dispersion. And that's because there's no polarity. There's no NH or OH bonds. And lastly, which molecule in each pair exhibits stronger intermolecular forces of attraction? Explain your choice and state the types of intermolecular forces acting on each. So here we're asked to compare water and ammonia. And if we draw water, we see that water has OH bonds, and I think we'll remember from ammonia that it has NH bonds. So both have all three. Both have hydrogen bonding, dipole-dipole forces, and dispersion forces. So which one has the stronger intermolecular force? Well, if again we think about the differences, we have an N and we have an O. We know that the O is more electronegative. And so we'd expect the OH hydrogen bonding to be stronger than the NH hydrogen bonding, and the OH dipole moment to be stronger than the NH dipole moment. And so H2O should have the strongest intermolecular force of attraction. How about HCl and HF? Both, of course, have dispersion forces. Both have dipole forces as well, because this bond is polar. H and Cl have different electronegativities. H and F have different electronegativities. But HF also has hydrogen bonding. Remember, we look for OH, NH, and HF types of bonds for hydrogen bonding. HF is a not very common type of hydrogen bonding because the only place to get it is in the HF molecule. So it's much more likely to see OH and NH bonds as hydrogen bonding, but HF also has hydrogen bonding. So certainly HF has the stronger intermolecular force. The last one is I2 versus Cl2. Both of these molecules are nonpolar, right? They have the same element on either end of the bond. And so all they have are dispersion forces. And the way to distinguish which is the stronger dispersion force is decide which has more electrons, I2 or Cl2. Basically, we can look at the periodic table. We see that iodine starts with 53 electrons for each iodine. Chlorine starts with 17. So we have over 100 electrons in the I2 molecule and only about 35 electrons in the Cl2 molecule. So for that reason, I2 has a much stronger dispersion forces than Cl2 because it has much more electrons. Clicker question 3.7. Which attractions exist between molecules in a sample of HF? Okay, so answering one of these questions, It's a molecule, so it has dispersion forces. That's always going to be true. There's always going to be dispersion forces present in any molecule. Is it a polar molecule? Well, H and F have different electronegativities, so yes, it is polar. So it could be dispersion and dipole-dipole. Does it have HF bonds, HO bonds, or HN bonds? Yes, it has HF bonds, and so it should have all three. And basically we could observe that it has HF bonds right off the bat. Therefore, it has hydrogen bonding. If a molecule has hydrogen bonding, it also has the other two. So the C is the best answer here.